Welcome to The Explainer. Today, we're diving into magnetism. And look, it's way more than just a trick for sticking stuff to your fridge. It is a fundamental power that literally emerges from motion itself, and it all starts with one simple question.
Right, so we've all heard of Coulomb's law. It's brilliant for describing the push and pull between charges that are just sitting still. But the second, and I mean the second, those charges start moving, that law just doesn't tell the whole story anymore. A brand new force just appears on the scene.
And yeah, you guessed it, that new force is magnetism. And it's a whole different ballgame. You see, unlike the electric force, it couldn't care less about stationary charges. It only affects charges that are on the move. And what's really weird is that its direction depends on how fast that charge is going and where it's headed.
So, here's our game plan for today. First, we're going to get to know this new force properly. Then, we'll see how it scales up from just a single charge to a massive current. We'll check out two really clever ways to calculate it, uncover the unbreakable laws that run the whole show, and finally, we'll reveal the quantum secret behind something as simple as a refrigerator magnet.
Okay, first things first. We really need to properly introduce this force that just pops into existence because of motion. And while its deepest, most fundamental origins are actually hidden in Einstein's theory of relativity, for our purposes today, we can just think of it as the fundamental partner to the electric force. Now, the key phrase here is relative to an observer. It's all about perspective. So if you were somehow moving right alongside a charge, you wouldn't feel any magnetic force from it at all. But for someone standing still, watching that same charge zip by, oh yeah, they'd feel a magnetic influence for sure. It's a force that is literally born from relative motion.
What's really wild is how this force works. It always, and I mean always, pushes sideways, at a right angle, to the direction the particle is moving. This means it can't speed a particle up or slow it down. In physics speak, we say it does no work. All it does is steer. So you can think of it like this perfect cosmic steering wheel, constantly changing a particle's path but never, ever touching the gas pedal.
So to wrap our heads around this weird steering effect, physicists came up with the idea of a magnetic field, or as they call it, a B field. It's this invisible field of influence that fills up the space around any moving charge. And when another moving charge happens to fly into this field, it feels that force, a force that depends on its own speed and the local strength of that B field.
Okay, so a single moving charge creates a teeny tiny magnetic field. Big deal, right? But what happens when you get trillions upon trillions of them flowing together, all in a nice, steady stream, kind of like water through a hose? Well, you get an electric current and a much, much more powerful magnetic field.
Now, to calculate the exact field from any wire, no matter what its shape, physicists developed this incredibly powerful tool, the Biot-Savart law. You can kind of think of it as the brute force method. It's not always pretty and the math can get hairy, but you know what? It will always give you the right answer.
The logic behind it is pretty straightforward. You just imagine the wire is made of a chain of teeny tiny little pieces. You calculate the magnetic field from each individual piece, and then you just add them all up. It's kind of like building a super high-resolution picture, one tiny pixel of magnetic influence at a time.
Now, while that Biot-Savart law always works, let's be honest, it can be a mathematical nightmare. So luckily, for certain situations that are really neat and tidy, like a perfectly long straight wire, physicists found a wonderfully elegant shortcut.
This is Ampere's law, and honestly, the insight it gives us is just beautiful. It says that if you draw an imaginary loop in space, the total amount of magnetic field you feel circulating along that loop is directly tied to the total electric current that is punching right through the middle of your loop. More current punching through means a stronger magnetic field circling around. It's that simple. So you end up with two really powerful ways of looking at the exact same problem. Biot-Savart is your universal brute force tool that always gets the job done. But Ampere's law, that's the elegant shortcut. It revealed this gorgeous relationship between the field around a loop and the current through it. It's a perfect example of what physics is all about, finding simple, profound patterns in a complicated universe.
Okay, so all of these calculations and observations, they ultimately lead us to two incredibly profound, totally unbreakable rules that govern every single magnetic field in the universe. And these are the real deal. They're actually two of the four legendary Maxwell's equations, which are basically the foundation of all of electromagnetism. The first rule sounds almost too simple, but its implications are massive. It's just this. You can't have a magnetic north pole all by itself, and you can never have a south pole all by itself.
They always, always come in pairs.
So, the direct consequence of this rule is that magnetic field lines can't just start or stop somewhere in space. They have to form continuous, closed loops. And that is exactly why if you take a bar magnet and you snap it in half, you don't get a north piece and a south piece. Nope. What you get are two new, smaller bar magnets, each with its own north and south pole. And that's true no matter how small you cut it.
All right, the second great rule. This one gets right to the very source of magnetism. It tells us exactly what creates these swirling, looping magnetic fields in the first place.
Okay, now don't worry about all the symbols here. What this beautiful little equation is really saying is that the source of a curling magnetic field, that's the part on the left, is an electric current, that's the J on the right. In plain English, where there is a current, there will be a magnetic field curling around it. No current, no curl. It's a fundamental law of the universe.
Okay, this is all great for wires and currents, but it brings up a huge question. What about a simple permanent magnet? You know, the kind on your fridge. It doesn't have a battery, it's not plugged into the wall, so where in the world is the current? Where's the moving charge?
Well, the answer is hidden deep, deep inside the atom. You see, every single atom has these natural, microscopic currents going on. First, you've got electrons orbiting the nucleus, which act like minuscule little loops of current. And even more importantly, every electron has this built-in quantum property called spin, which basically makes each one act like a tiny, spinning magnet all on its own.
Now, in most materials, say a piece of wood or plastic, these trillions of tiny atomic magnets are all pointing in completely random directions. Their effects all just cancel each other out, so material seems not magnetic. But when you bring a strong external magnetic field nearby, it's like a drill sergeant shouting attention. It can convince all those tiny atomic compasses to snap into alignment, and suddenly the whole material becomes magnetic.
And this alignment happens in a few different ways. Some materials are actually weakly repelled by a field, others are weakly attracted, but then there are a special few, like iron, that are ferromagnetic. These guys have a powerful quantum effect that can actually lock their atomic magnets into alignment, creating a strong, permanent magnet long after that external field is gone.
So here it is. Here's the crucial takeaway. There is no fundamental difference between the magnetism you get from a current in a wire and the magnetism from a permanent magnet. At the most basic level, it is all just moving charges. The universe doesn't see a difference, it just sees current, whether that's electrons flowing in a copper wire or the quantum spin of a single electron.
And that leaves us with one final, fascinating thought to chew on. The fact that the electric and magnetic forces are really just two faces of the same coin, a single phenomenon called electromagnetism, whose appearance changes depending on how you're moving. Well, it points to this profound unity at the very heart of physics. And it really makes you wonder, doesn't it? What other fundamental forces that we think are totally separate might just be a different perspective on something we already think we know?